I'm Dr.L.Prasanna Venkatesh, Department of Mathematics, Sathyabama Institute of Science and Technology, deemed to be university. In this video, I'm going to discuss conditional probability and Bayes' theorem. For that, let us recall some of the properties of probability, which is probability of A union B is equal to P of A plus P of B minus P of A intersection B. And probability of complement of any event is 1 minus probability of that event. Also, let us discuss about mutually exclusive events. Mutually exclusive events are events which will avoid other events when those events are happening. So, if we consider A and B as two mutually exclusive events or two events of a random experiment, they are said to be mutually exclusive if happening of A will avoid happening of B or happening of B will avoid happening of A. In that case, what will happen? Suppose A happens, then B will not happen. If B happens, A will not happen. It means A and B simultaneously cannot occur. So we can say number of possibilities in which A and B occurs simultaneously is 0. N of A intersection B is 0. If N of A intersection B is 0, we know that probability of an event is number of favorable occurrences divided by total possible number of occurrences. Since numerator is 0, its probability will be 0. So to conclude, we can say two events are said to be mutually exclusive if and only if probability of A intersection B is equal to 0. It means if probability of A intersection B is 0, we can say they are mutually exclusive events. If they are mutually exclusive events, then probability of their simultaneous occurrence is equal to 0. Next, we will discuss what is conditional probability. Let us consider two events A and B associated with the same random experiment. The probability that A happens given that B has already occurred is called conditional probability of A given B, and it is denoted by P of A slash B read as probability of A given B. Since it is given that B has already happened, the total sample space will reduce to probability of B or the region that involves B alone. Now, within this region, we also want A to happen. So, what is the favorable occurrence? The favorable occurrence will be already B has happened and we also want A to happen. So, it is A intersection B. So, A intersection B is the favorable occurrences and B is the total possible occurrences. So, B will be the sample space, A intersection B will be the favorable occurrence. We can easily see from the diagram that B has already happened, it is given. So, our focus shift from the entire region to this circle of B alone. Within this, we want A also to happen. So, this is possible in A intersection B. So, this violet color divided by the total circle of B will be our probability ratio. So, P of A given B is number of occurrences of A intersection B divided by N of B. We can divide both numerator and denominator by N of S, and after dividing, N of A intersection B by N of S becomes probability of A intersection B, N of B by N of S becomes probability of B. So, P of A given B is P of A intersection B divided by P of B. Same way, P of B given A will be P of B intersection A divided by P of A, but intersection A intersection B, B intersection A, both are same. So, we can denote it as P of A intersection B by P of A. What are independent events? Unlike mutually exclusive events, independent events are events which will not depend on the happening of the other events, which means if we consider two events A and B, if the happening of A does not depend on the happening of B and happening of B does not depend on happening of A, we call the events as mutually independent events. Hence, if we consider conditional probability of A given B, it is not going to affect the probability of A. So, probability of A given B will be same as probability of A. Already we know probability of A given B. It is P of A intersection B divided by P of B. By using this, we can cross multiply and get the result as P of A intersection B is equal to P of A into P of B, which means if A and B are independent, we get that P of A intersection B is equal to P of A into P of B. Same way we can backtrack and say if P of A intersection B is P of A into P of B, we can say A and B are independent. In short, what we can have as two important results for mutually exclusive and independent events. If P of A intersection B is 0, two events are mutually exclusive and vice versa. And P of A intersection B is equal to P of A into P of B is equivalent for independent events. Let us go for a problem. A statistical problem is given to three students A, B, C, whose chances of solving them are 1 by 2, 2 by 3, 3 by 4 respectively. If the problem is given to all of them and they are trying independently, what is the probability that none of them solves the problem? What is the probability that the problem is solved, and what is the probability that exactly one of them solves the problem? For solving this problem, we need to recall one property, that if A and B are independent, then the complement of the events are also independent, and one particular event with any other combination of other event or its complement will be independent. For example, if A, B, C, three events are independent, then A will be independent of B or B complement, C or C complement, like any combination. So first let us try to symbolize the informations. Let A be the event of A solving the problem. Likewise, B will be B solving the problem, capital C will be C solving the problem. And A complement, denoted as A bar, A power C or A bar, both represents complement of an event. So here we are denoting it as A bar. A bar represents event of A not solving the problem. Same way B bar will be representing B not solving the problem. C bar will be representing C not solving the problem. It is given that probability of A is half, then complement is 1 minus. 1 minus half, which is 1 by 2. P of B is 2 by 3. P of B complement will be 1 minus 2 by 3, which is 1 by 3. P of C is 3 by 4 and P of C complement will be 1 by 4. Now what is required? Let us try to convert them in terms of probability terms. The first question, none of them solves the problem. None of them solves the problem can be mathematically converted into A not solving the problem and B is not solving the problem and C is not solving the problem, symbolizing A complement and B complement and C complement, and can be mathematically converted to intersection. So we can write this as A complement intersection B complement intersection C complement. As I already told you, if A, B, C are independent, it is given in the question, they are trying the problem independently. Therefore, the complements are also independent by property. Second question, problem is solved. When will be the problem is solved? If any one of them solves the problem is solved. A solves the problem, or B solves the problem, or C solves the problem. The same question can also be coined as, what is the probability that at least one of them solves the problem? A or B or C. And the mathematical operator connecting OR is union. So we can write this as P of A union B union C. But instead of looking at it like this, there are two possibilities. The problem can be solved or the problem is not solved. If the problem is not solved, it means that none of them solves the problem, which reduces to the first one. So it is complement of the first one. The first one says none of them solves the problem. The complement of it, at least one of them solves the problem, which is problem is solved. Therefore, the second one can be looked at as A union B union C, which is 1 minus P of A complement intersection B complement intersection C complement. Then the last one, exactly one of them solves the problem. A solves the problem, B and C not solving the problem, first possibility. B solves the problem, A and C not solving the problem, second possibility. C solves the problem, A and B not solving the problem is the third possibility. So all these out of these three, any one can occur and all these are mutually exclusive. Therefore, we will have it like this. Since they are mutually exclusive, we can add the probabilities for calculation purpose. Now, proceeding for the first one, P of A complement intersection B complement intersection C complement. Mutually independent is product of the individual probabilities for intersection of probabilities. So, intersection B intersection C intersection can be written as product of their individual probabilities, P of A bar into P of B bar into P of C bar. We already know the values. Substitute the values, we get 1 by 24 as probability of none of them solves the problem. Second one, A union B union C. Already we discussed it is complement of none of them solves the problem. So we already have the value as 1 by 24. Substituting, we get 1 minus 1 by 24, which is 23 by 24. Third part, exactly one of them solves the problem. We can write it as A intersection B bar intersection C bar, etc. up to the third one, and this is equal to sum of each of these probabilities as they are mutually exclusive. And these individual probabilities can be calculated in the same way like the previous ones. Since they are independent, probability of intersection is product of their individual probabilities. So it is P of A into P of B bar into P of C bar plus etc. till the last term, which is equal to, just I am substituting whatever values we got in the previous slide. If we substitute and simplify, we get the value as 6 by 24, which reduces to 1 by 4. So far we have discussed conditional probability and independent events. Now we will discuss an example, and based on that example we will discuss two more theorems. There are three sections: section A, section B, section C. Each section has got certain number of boys and certain number of girls. And the experiment goes like this. You are going to randomly select one class, and from the selected class you select one student. So this is the experiment, and the composition of boys and girls are like this. Section A has got 20 boys and 30 girls. Section B has got 25 boys, 25 girls. Section C has got 40 boys and 10 girls. So the compositions are like this. In class A, there are more girls. In class C, there are more boys, and class B has got equal number of boys and girls. According to this experiment, one will be interested to know what will be the end result of this experiment. And what is the end result of the experiment? We are first selecting class. From the class you are selecting a student, and that student may be a boy or a girl. That is the end result. So the first question is, what is the end result? And the end result of this experiment, it's a boy or a girl, and its probability is known as total probability. Then what is the cause for this result? The cause for the result could be the class we have selected. We have said either we would have selected the first class. If we have selected first class is having more girls. There is more chance for a girl to be selected. If we select third class is having more boys. So if we select third class, there is a chance that a boy can be a final selection. So like that, the cause for the entire result may be which class we are selecting. The probability of the first one is called probability of the effect. Whenever we are calculating probability of the end result, that is probability of effect. And the probability of the second one is called probability of cause. Probability of cause is found by Bayes' theorem, and probability of end result or probability of effect is calculated by theorem on total probability. So we symbolize or pictorially represent the given situation in this way. So we have B1, B2, B3, etc. up to Bn of a circle which are sectors. B1 is a sector, B2 is a sector, B3 is a sector, etc. up to Bn is a sector. This is the outer circle. There is an inner circle. The total of the inner circle is called A. And this inner circle certainly will have intersection with each of the B1, B2, B3, etc. up to Bn. So we denote the first one, the intersection of A with B1 as A B1. It is in terms of symbol A intersection B1, and the second one is A intersection B2, which is A B2, etc. up to A Bn. So if we see this inner circle, it is union of A B1, A B2, A B3, etc. up to A Bn. So we call these events as mutually exclusive and exhaustive. B1 to Bn are mutually exclusive and exhaustive, and this event A, the inner circle, is an event that is associated with each of these B1 to Bn. So this is the general setup of this experiment, and we want to know the end result, probability of A. A is happening. So we have already taken A as the end result or the required event. So probability of A could be because of B1 or because of B2, etc. up to because of Bn. And P of A is given by the formula I is equal to 1 to n, P of Bi, P of A given Bi. We are considering B1 to Bn as mutually exclusive and exhaustive events as described in the diagram. What we want is probability of A, and we know that A is union of all these mutually exclusive and exhaustive inner sectors AB1 to ABN. So I can write A as A intersection B1 union A intersection B2 union, etc. up to A intersection Bn. So we can write like this. Since they are mutually exclusive, we already know when the events are mutually exclusive, probability will be sum of their individual probabilities. So P of A is equal to P of A intersection B1 plus P of A intersection B2, etc. up to P of A intersection Bn. This I can write summation over I P of A intersection Bi. Already we have conditional probability. Conditional probability of A given Bi. It is P of A intersection Bi by P of Bi. If we cross multiply, we get P of A intersection Bi to be P of Bi into P of A given Bi. Substitute this here, we get the required result, and this is the final result we want to prove. Next we will discuss Bayes' theorem. Bayes' theorem is probability of finding cause. Given that A has happened, what is the probability that it is because of Bi? And that is given by P of Bi into P of A given Bi divided by summation P of Bi into P of A given Bi. It is the same experiment that we considered for theorem on total probability. Only difference, instead of calculating P of A, we are calculating P of Bi given A. And how this can be proved? By conditional probability, we have P of Bi given A is P of Bi intersection A by P of A. P of A given Bi is P of A intersection Bi by P of Bi. We can rewrite this as P of Bi intersection A by P of Bi. Now cross multiplying, we will get P of Bi intersection A as P of Bi into P of A given Bi. From 1 and 2, if we substitute, we get P of Bi given A is equal to P of Bi given A divided by P of A, which in turn can be written as P of Bi into P of A given Bi divided by P of A. By theorem on total probability, already we know P of A is summation P of Bi into P of A given Bi. So this is the proof for Bayes' theorem. Now let us try to apply this in a problem. There are three machines, machine A, machine B, machine C. They produce 25%, 35%, 40% of the total production, and it is also given that 5% of machine A will be defective. Whatever produced by machine A, 5% of that will be defective. Whatever is produced by machine B, 4% will be defective. Whatever is produced by machine C, 2% will be defective. And the combined output is taken and one bolt is chosen at random. What is the probability that if we find that it is defective, it is produced by B or C? Which means individually for B we need to find probability, for C we need to find probability. Let us try to symbolize this information. Let AB bolt is produced by machine A. Likewise for B and C. For B, bolt is produced by machine B. For C, bolt is produced by machine C. From the question, it is given that out of total output, 25% is produced by A. So we can take it as 25%, Convert it in terms of fraction, it is 25 by 100, which is 0.25. Same way for B, it is 35%, 0.35. For C, it is 40%, 0.4. These are the probabilities of A, B, C. Supposing it is given that you are going to select a bolt from bolts produced by machine A. We know that 5% of total production by A is defective. So that we can consider first D as selecting a defective bolt, then the conditional probabilities of selecting defective bolt given that they are produced by A or B or C. Given that you are going to select from machine A's production, it is defective will be 5%, and 5% in terms of value will be 0.05. Given that you are selecting from B, it is defective is 4%, that is 0.04, and that for C is 0.02. Now we are tabulating all these informations. Like we have BI, it is either machine A or machine B or machine C, and then probability of BI, it is P of A is 0.25, P of B is 0.35, P of C is 0.40, and these conditional probabilities D given A, D given B, D given C, 0.05, 0.04, 0.02. Just multiply. This third column gives you P of BI into P of A given BI. Just multiply and add. The sum by theorem on total probability, summation P of BI into P of A given BI is P of A. P of A we get it as 0.0345. By Bayes' theorem, probability of A given it is defective will be 0.125 divided by 0.0345, because P of BI given A, we have the formula. That formula states that it is P of BI into P of A given BI divided by the summation, and that is this particular value divided by the total. It is the probability of cause for A, and 0.0140 divided by P of A is probability that given it is defective, it is produced by machine B. And this 0.0080 divided by 0.0345 is probability that it is produced by C given that it is defective. So probability given that it is defective, it is produced by A will be 0.0125 divided by 0.0345. Simplifying, we will get 25 by 69. Same way, P of B given D will be 28 by 69, and that of C given D will be 16 by 69. In the problem, it is asked for B or C. So for B, it is 28 by 69. For C, it is 16 by 69. Hope you have understood what we have discussed so far. Thank you.